Now we will see how to do the fault calculations using the impedance matrix. Okay. So how is the impedance matrix related to the bus voltages and current? V is equal to Z into I, right, where V is the column matrix of all of the voltages at each of the buses, right. So at bus 1, let's say voltage is V1, next at bus 2 voltage is V2, and so on till Vn. So this is an n into 1 matrix where n is number of buses in the power system network. Okay. And similarly, I will also be a column matrix, I1, I2 and so on till In. This is also n by 1 matrix. Okay. So then what will be the order of Z? Z is going to have order n into n. Now before we go into the fault calculation, we will discuss a few basic relationships. Okay. So the first relationship is this, V is equal to Zi, this is the basic relationship, right. Next, if there is any change, a fault is nothing but a change in the currents and the voltages, right. There will be some fault current, and because of which there will be some changes in the bus voltages. Okay. So we are going to take any general change. So in case of a change in current injected into bus R, let us say we are just taking a random number of the bus. Okay. So all of these currents that we are taking here, this will be the current injected into the transmission system through the bus, right. So now what will happen in case of any change in any current injected? All of the voltages, all of the bus voltages are going to change. Okay. So the bus voltages will change. Okay. So if you want to write this in mathematical form, then what will it be? V1 plus delta V1, V2 plus delta V2 and so on till Vn plus delta Vn. This will be the new voltage matrix, and this will be equal to, you can write Z11, Z12 and so on till Z1n, and we will take the rth row. Okay. So what will be the rth row? ZR1, ZR2 so on till ZRn, and the last row anyway Zn1 to Zn, right. This will be the impedance matrix, and the current injected in the bus R, only that is changing, everything else is remaining same. Okay. So here you are going to get I1 plus 0, I2 plus 0 and so on till IR is experiencing a change in current. So IR plus delta IR, and the last element will be In plus 0. Okay. Here also you can take, in the voltage matrix you can take VR plus delta VR. Okay. Now this is the equation. Now what we can do, we can write this matrix as V matrix, the original V matrix, V1, V2 and so on till Vn, plus the change in voltages, right, delta V1, delta V2 and so on till delta Vn. So this will be equal to the Z bus matrix, I am not writing the elements again, into, here you can take another bracket here, the current matrix also you can divide into two matrices, right. So what will be that? I1, I2 so on till In plus 0, 0 so on till, here you are going to get rth element will be delta IR, and everything else is going to be 0, right. So this entire thing you are multiplying with the Z bus matrix. Now this in matrix form is going to be V plus delta V, right. This is the voltage matrix and this is the change in voltage matrix. Okay. And then this will be equal to Z, the impedance matrix, into I plus delta I. Okay. Because here you can take each of the changes is equal to 0, right. So that is how you can take this as I plus delta I. Then what you are going to get? V plus delta V is equal to Zi plus Z delta I. But we know that V is equal to Zi. So from here what you are going to get? Delta V is equal to Z delta I. Okay, since V is equal to Zi. So this is the second relationship that is important. Next we will consider a power system network. So here you can take a particular bus R. Okay, so this is bus number R, and this you can write power system network. This is okay, it has a number of buses inside it. Now if you look through these terminals, there will be a ground also, right? So if you take this as the reference bus, now you want to look through the bus R and you want to find out the Thevenin's impedance. Okay, ZTH. This is going to be the ZRR element in the Z bus matrix. Okay, so you can write here, this is the rth row, rth column element in impedance matrix. Okay, so this is another relationship that you need to know. You can take this as a third relation. Now we will come to the actual fault calculation. So let us take a power system network here, and the fault, it has occurred at bus R. Okay, so if you consider bus R here, this is now shorted to the reference node, right? This is how a fault will look like. Now sometimes the fault, it will have some impedance associated with it. Okay, so if nothing is given, then you can simply take 0, right? But if not, if some fault impedance is given, then that we are considering as ZF. Okay, so now the current through this is IF, right? The fault current. So this is the fault current. Now we have to find out this fault current. Okay, also you note down that this is the fault impedance here, otherwise it will be confusing, right? Now here we will consider pre-fault voltages. So for fault calculation we need the pre-fault voltage, right? So here let pre-fault voltage matrix be V naught. We are representing as V naught. So this is what it will be equal to V1 naught, V2 naught, and so on till Vn naught. Okay, and next post fault voltages. Post fault voltage matrix. So this is going to be represented as Vf. Now what will this be? This is going to be the initial voltages plus the change in voltages. So this we are going to represent as V1f, V2f, and so on till Vnf. Now what about delta I, the change in currents? Okay, so here we have a fault current that is extra at bus R. Now all of the currents we take as injected into the bus, right? So but this is coming out of the bus. So what will be the change in current at bus R? It is going to be minus IF. Okay, so change in current at bus R, this is going to be delta IR, which is minus IF, and negative sign because IF is coming out of the bus. Okay, so now we will make use of the second equation. What was the second equation? The change in voltages delta V will be equal to the impedance matrix into the change in currents. Okay, so we know delta V is equal to Z into delta I. So if you write the entire matrix form, what will this be? Delta V1, delta V2, and so on till you are going to get somewhere here delta VR, and so on till delta Vn, right? So this is going to be equal to Z11 so on till Z1n. Okay, and similarly you have the rth element, rth row, ZR1, ZR2 and so on till ZRn. The final row is going to be Zn1 and so on till Znn. Now what about the change in currents? Only the rth current, rth bus current is going to change. Everything else there is no change. So you are going to have 0, 0 so on till delta IR is going to be minus IF and so on till 0. Okay. So if you write the equation for the rth row, what will this be? This is equal to delta VR is equal to this row into this column. Right, now all of the elements here are 0 except the rth element. Okay, so delta VR is ZRR, right, that is the element, rth element, into minus IF. Okay, so now this is the change in voltage at the rth bus. So you can write the voltage, the post fault voltage at rth bus, post fault voltage at rth bus. This is VRF is equal to VR naught plus delta VR. So this will be equal to VR naught minus ZRR IF. Now what will be VRF here? If you see this diagram here, the post fault voltage is nothing but this here, right, VRF. Now what will this be? This is equal to IF into ZF, right. So you can write here ZF into IF. Now from here you can find out the fault current. So what will be the final expression? IF is equal to VR naught divided by ZF plus ZRR. Okay, so you need to know if you want to find the fault current, then you need to note the pre-fault voltage at that bus VR naught, and you need to know the fault impedance and the ZRR element of the impedance matrix, which is nothing but the Thevenin's impedance. So ZRR, if it is given in the matrix, well and good, otherwise you just have to find out the Thevenin's impedance seen through that bus. Okay. Now what if the fault impedance is 0, that is ZF, that is 0, then simply IF will be equal to VR naught by ZRR. That means the pre-fault voltage divided by the Thevenin's impedance. This is what we already know, right? This is what we have. This is how we have been finding out the fault current in the symmetrical faults. Now once we found out the fault current, we can find out the post fault voltages at each of the other buses, right? The voltages are changing now. So the post fault voltage, at any ith bus, okay, this can be found as VIF. What will be VIF? This is equal to the pre-fault voltage plus delta VI, okay, and this is equal to VI naught. Delta VI you can find from this equation, right? So any delta VI if you are taking, you are going to get ZIR into minus IF, okay. So you can verify that later. This is going to be plus ZIR into minus IF. Now we know the fault current, we have already found the fault current. So this is VI naught minus ZIR VR naught divided by ZF plus ZRR. Okay, so this is the expression for any ith bus. That means not just the bus where the fault is occurring, any other bus. Okay, so this is how you find out the fault current as well as the post fault voltages using the Z bus impedance matrix.